Welcome back, Chemistry Theory. This is the last video here, the part 3 with covalent bondings. So we looked at distances between two atoms when they have various bonds. So if we take a look here, a single bond between nitrogen, double bond between nitrogen, triple bond between nitrogen, you can see a relative length here. The angstrom is kind of a weird unit, means times 10 to the negative 10. Just simply look at the number though. Obviously, the more bonds we have, the smaller the number we have. So we can take a look here as a reason. As a general rule, the length of the bond between the atoms decreases as the number of shared pairs increases. So let's just highlight that, decreases. And we can kind of think of that, I added it in here. So the length of the bond between the atoms decreases as the number of shared electrons increases. We can think of the more electrons we have, the more glue we have holding it together, using the idea that the electrons between two nuclei act as the glue, attracting those two nuclei close together, making that covalent bond. So the more glue we have, the closer these atoms will be, single bond, double bond, triple bond, etc. That gives us a reason as to why the lengths between them, the separation gets smaller and smaller when we have more bonds, because we have more electrons there. So if we look here, the CO bond length in carbon monoxide is 1.13 angstroms, whereas the carbon-oxygen bond length in CO2 is so between the carbon and oxygen is 1.24. Without drawing a structure, do you think that CO contains a single, double, or triple bond in each of these, in carbon monoxide versus CO2? If we compare the numbers just to the nitrogens here, we can kind of get an idea, like 1.13 here. Hey, that could be a triple bond. And over here, 1.24, hey, that's close to a double bond. So we could reason here that the bond length between carbon monoxide, hey, it could be a triple bond between carbon and oxygen. And over here, the carbon between one carbon and one of the oxygens in CO2, 1.24, so hey, it could be a double bond. I did draw them out here, and there's something interesting that happens here. If I look at CO, now, of course, there's a problem here that develops. Carbon is 4, oxygen is 6. So oxygen needs 2 more, carbon needs 4 more. So it seems like we can't make it work when we just have carbon and oxygen. But yes, it does form a triple bond as predicted over here, because the length between carbon and oxygen is small, 1.13 angstroms, similarly to 2 nitrogens, which we know for sure is a triple bond. But what happens here, and we'll look at this later on in detail, there's a coordinate covalent bond that forms here. So carbon shares 2 to get to, so these two are shared, 1, 2 at the bottom. But oxygen actually donates an extra set, and that's referred to as a coordinate covalent bond, in which one atom supplies an electron pair. So if we take a look here, when all is said and done, carbon has 2, 4, 6, 8, and oxygen would have 2, 4, 6, 8 as well. So the tricky part with that one is that we introduced the coordinate covalent bond. We're going to look at that again. So carbon donates 2, each oxygen donates 2, but oxygen has 2 extra left over which it donates so that carbon can have the 2 that it needs to get an octet. Carbon dioxide is a little bit easier. So oxygen needs 2. Oxygen needs 2, carbon needs 4, so if it donates 2 with this oxygen, donates 2 with this oxygen, everything will have an octet. That oxygen's good, that oxygen's good, and looking at what's between the carbon and oxygen, 2, 4, 6, 8, that carbon is good too. So just represent that with lines. This triple bond here, 2, 2, and 2, line, line, and line. So the predictions here coincide with what happens here. So the very short distance between the carbon and oxygen signify a triple bond, and the larger distance, 1.24, between this carbon and oxygen, or this carbon and oxygen, signify a double bond. Alright, that is the end of section 8.3, covalent bonding.